This is the revision video on the first module, module 1, which is electric current of G482, which is electrons, waves and photons exam for AS level. So let's start by thinking about this simple electricity problem. We've got a circuit that's about the size of the school, and on one side of the school I've got the switch, and on the other side I've got the light bulb. And so we start by asking the question, if I was to switch it on, what kind of delay would there be? Would there be no delay whatsoever because it happens instantaneously? There'd be some small delay or some long delay, and you'll be asked to think about this problem in your first lesson. Now, the reason most people think that there will be some kind of short delay is because they think that the electrons have got to travel right the way from the cell all the way around to the bulb, and in reality that doesn't happen, because we often think about lightning and those kind of things, and it's not really like there's like a stream of lightning travelling down the wire. It's not a particularly helpful model. So that's one of the first things we need to do. We need to develop sort of a more consistent model with how electric current flows along a wire in order to answer this question. So, the module electric current. We're going to start by talking about what electric current is and defining the Coulomb. We're then going to learn about Kirchhoff's first law and how that relates to conservation of charge, and then we need to be able to explain mean drift velocity and apply the equation for that. So you should have read the module as a sort of prerequisite to watching this, and you should recall what you learned about GCSE electricity. So this is what the specification asks of us. You might want to pause it for a moment and just have a quick read through the kind of things that we're going to cover, and then use this to check at the end to make sure that you understand everything. So, electric current. This is again just a breakdown of the different aspects of this module. Okay, so if we think about a simple circuit like this one, we've got, in this case, a battery, a bulb, and we've got a wire. Now, the first question then is, what is electricity? Now, when we talk about electricity, what we mean is that there is a charge carrier that is flowing through some kind of conductor. Now, that could be a wire. It could also be an electrolyte, or it could be a liquid. And I'm also ambiguous with the phrase charge carrier. Some people will say that it is the flow of electrons, but it doesn't have to be electrons that are in fact carrying our charge. It could be ions that are moving. So electricity is the movement of a charge carrier through a medium. So what we're talking about when we say in a charge carrier, we're talking about electrostatic charge, so either positive or negative. Now electrons obviously have a negative charge. Now on the battery, as an example, we've got the two terminals. We've got the positive and we've got the negative. Okay, and in this notation actually is two cells, which obviously a cell is a single unit, and more than one creates a battery. And so on this battery, on this cell as well, we get positive and negative. So overall we've got the positive and the negative terminals. So in the wire we're going to have the charge carriers, which are our electrons, and they're going to transfer the energy from the battery to the bulb. Now the current is the flow of electrons that travels through the wire. So the more electrons that I have flowing per second, the greater the current. Now the direction of the current flow goes from positive to negative. Okay, so it goes that way around. That's how we conventionally describe current flow. Now if you think about that for a minute, you may think that I've lost my mind and that I'm making a mistake, because you should realise that electrons are negative, so they will in fact be attracted to the positive terminal. So the electrons will flow in the opposite direction. Okay, they will flow that way around. So electron flow and what we call conventional current are two very opposing ideas, and the reason for this is really simple. In order to discover electrons in the first place, we had to use machines that require electricity. So we had an understanding of electricity in terms of how it operated and how it worked before we'd actually discovered what an electron was. So we basically had a 50-50 chance of deciding what way around a circuit electric current went, and we basically got it wrong. But it has stuck, and so that whenever we're talking about current flow through a circuit, we always talk about it in terms of conventional current, not electron flow. And the last question then, why does current flow in the first place? Well, the reason is because we have a source of energy in the form of the cell, and we call the energy across this, the change in energy, the potential difference, which is commonly called the voltage. So we'll be talking a little bit more about that in a little bit. So current then. So a current will flow if we've got an unbroken circuit. If I have got a broken circuit, current can still flow. It just means I have to put a significantly larger potential difference across it. So we define current as the rate of flow of charge. Now remember, rate means per time. So I can get an equation from that straight away, in the sense that I should be able to recognise that if we're saying that current is charge per unit time, I get this equation. So this is what I sometimes call the quit equation for short to remember. So the flow of charge, or the change in charge, is equal to the current times the change in time. The units for each of these, so charge has got units of coulombs. Current, which is given the symbol I because it used to be named electrical intensity, which is why it's used an I. It's got the unit amperes, or amps, and then time is obviously measured in seconds. So from that, if we're defining a coulomb, then what I can say is that 1 coulomb is equal to 1 ampere second. And so I could obviously do that another way, as I could define an ampere as 1 ampere is equal to 1 coulomb per second. So that's what we mean by current. If I've got 1 ampere of current, I've got 1 coulomb's worth of charge flowing every second. Now there's an example for this. This is the question. A current in a lightning strike is 7,800 amperes. The strike lasts for a time of 230 milliseconds. Calculate the charge flowing between the cloud and the grounds and the number of electrons transferred. So the first question should be fairly straightforward. We've got a time and we've got a current, so we simply need to work out the charge. So we're just going to use our quit equation. Okay. The second one, we need to sort of add an extra equation to work out. So I use my quit equation. I write down my information and put my equation, put my numbers in, and I get an answer of 1.8 kilocoulombs. Now the second one, if I want to work out how many electrons have been transferred, what I need is I know the total. I know the total charge that's been transferred, and I want to work out the number of electrons. So I can use this equation, but the number of electrons is going to be the total charge Q that's been transferred divided by E, where E is the charge on one electron. Okay, and E is given this value here, which is 1.6 times 10 to the minus 19 coulombs. That's the charge on one electron. So I divide the two by each other using that equation, and I get an answer of 1.1 times 10 to the 22 electrons that have been transferred in this lightning strike. As a slight add-on to this, we use different metals for different components and different parts for various reasons, as we'll discuss later. But I'm just going to flash these up, and you can take your time to think about them briefly, and we'll discuss some of these in class. Okay, so if we look at copper and we look at the current flowing through it, what we'll see is that it's a crystalline structure, and we can see copper crystals being grown here via electrolysis, and that means that the atoms are arranged in rows as a lattice. Okay, we can see that as a diagram here. So you should be familiar with this idea of metallic lattice. So we've got the positive cations, our positive ions here, and our sea of delocalized conduction electrons. And in this case, copper, each copper atom provides one conduction electron. Now, the electrons in there are free to move, and they will move randomly, okay, depending on their temperature, their temperature is linked to their random kinetic energy. So they're never standing still. They're electrons, they haven't got legs. They're never staying still. So they're going to move around. So I will answer this question first, and then come back to that point. So in terms of instruments that we use in electric circuits, if we're measuring electric current or potential difference, we measure electric current with an ammeter, potential difference with a voltmeter. This is just asking what the symbols of this represent, which you should be able to answer for yourself. And then there's another question there. I'd have a go at them and then move on. And the answers are here. You should be able to work those through nice and easy. So the difference between the following, then going back to the point, is that we've got this random movement of delocalized electrons, and you can see, if I compare that to this diagram, you can see this is very random. The electrons are colliding with the ions in the lattice as they're moving around, but there's no net movement in any particular one direction. In this one, despite the random movement, there is a drift along the wire in this direction. So this is the path of a conduction electron when there is no current flowing. This is when there is a current. Okay, so when a potential difference is applied across the wire, that's causing the electrons to flow, which we can describe as the mean drift velocity. So just a couple more questions on charge then. State what is meant by electric current. A mobile phone is connected to a charger for 600 seconds. The charger delivers a constant current of 350 milliamperes during this interval. Calculate the total charge supplied to the mobile. You should pause it and then answer these questions. So the answers then, for the first one, we define it as the rate of flow of charge. That's what we mean by current. And then again, just using the question, the Critt equation, we get an answer of 210 coulombs. A couple more questions here for you to have a go at. Again, I'd pause the video and then work through them and then check your answers afterwards. So the answers to those questions are as follows. If you're unsure about any of those, please make sure that you ask in class about them. So ammeters are what we use to measure current, and we connect ammeters in series to our circuit. Now, they effectively just count the amount of charge flowing past a particular point in a particular second. So we define an ampere as 1 coulomb per second, and it's really important that because we're connecting the ammeter in series, that it has a negligible resistance, because if it had any appreciable resistance, then what would happen is we'd get potential difference across the ammeter, and so some of our energy would be lost to the ammeter, and that would affect the rest of our circuit. And so the process of measuring must not directly impact what you're measuring, because if we had a resistance, the current would actually drop as a result of the fact that there was an ammeter there, and so we'd get false readings. That's the end of the first lesson on electric current. The next topic is Kirchhoff's first law. So you should watch this video you should watch the next video on Kirchhoff's first law prior to your next lesson.